Let's start looking at specific eigensolutions. Start with the equatorial Rossby waves. Looking at the general dispersion relation we plotted just now, remembering Rossby waves are low frequency waves of all, so we can look for asymptotic solutions. So you can simplify the equation in this way, where omega squared is much less than 1. So this relation, the dispersion relation, becomes simpler. We still have the meridional modes, we still have the Doppler shifted frequency term and the basic state, but we just dropped the omega d squared over c squared term, and that's about the only change. So then the Doppler shifted frequency as a function of zonal wave number, meridional modes, and the basic state along with beta squared becomes this complicated looking thing, where r, this r in here, is this function. Okay, so these are longish expressions, so I'm not sure I can give much insight on those other than to see what specific impacts are there when k is large, n is large, and so on and so forth. Okay, and c of course depends on the depth as well. So it's easier to just jump to a couple of solutions and see how eigenfrequencies of this equatorial Rossby wave changes when you change the background state or the basic state. Okay, the term basic state and background state are used interchangeably. So here it says n equals yes, it's n equal 1, but I think somewhere it was mislabeled here. So n equal 1 and n equal 2. Okay, so two modes are plotted here, but the equivalent depths or the depths of the fluid are changed from 50 meter to 300 meters. Unfortunately here the sign of the velocities has been changed. So you expect that a westerly flow, which is this one, will increase the frequency as the wave number increases, and it increases the turning latitude or the wave number where the low frequency mode changes into a high frequency mode, or the westward phase speed begins to become eastward short Rossby waves versus long Rossby waves, and so on. So you can go through the relation and plot this yourself to make sure that you know how a westerly basic state changes the wave number and frequency of equatorial Rossby wave versus a easterly basic state. A westerly basic state reduces the beta effect, expands the equatorial trapping width, and so on for the same same depth and for the same mode. So you can see here n equal 1, n equal 2 for easterly flow, for resting state, and so this is westerly, this is easterly. Just remember that the colors have been switched. And there is a dramatic effect when you increase the depth. Again, increasing the depth increases the equatorial trapping latitude, or the turning latitudes extend further out, so the influence of the waves expands out, and that is seen here as well in terms of the wave number frequency relation. So this is the modulation we talked about when we derived the Doppler frequencies, of course. Okay, so wave number modulation, frequency modulation happens because of the background state changes. You can also look at the group velocities for different modes and different equivalent depths, and you can see that they are mostly negative or westward, except in some cases they turn eastward, short Rossby waves at some wave number, but that turning changes in terms of wave number as you increase the water depth. So you can see that this zero crossing here is shifting to is it shifting? Well, it's still at the same, approximately the same wave number, but the eastward velocity here is larger. So this is the Doppler shifted group velocity depending on the fluid depth and the background state. What do you what do you want to get out of this? That once we derive the dispersion relations with the basic state, constant basic state, we can look at the impact of the basic state and the fluid depth on the wave number and frequency. So that's the modulation we had already talked about. You can also look at the critical wave number where the transition happens. So equivalent depth and wave number, looking at the group speed. So this same information here is drawn for different meridional modes. So remembering n is 1 and 2 here. First Hermite polynomial or meridional mode, second polynomial mode, and the zonal group speeds are written here in meters per second, and you can see that there is a change in the critical wave number where you go from eastward group velocity to westward group velocity. Okay, so the character of the waves themselves changes obviously when you have interactions with the background state and when you increase the fluid depth. So this is showing ER Doppler shifted group speeds for n equal 1 and n equal 2 as a function of zonal wave number for different fluid depths, group velocity as a function of wave number and depth for again n equal 1 and 2. The bold red line here, right, is where CGX is 0 contour, so the group speed changes direction. Bold blue contours are where the group speed reaches westward 10 meter per second, suggesting that in the region of upper tropospheric westerlies, we will see that in a minute, when the upper tropospheric winds in the tropics have westerlies and you have group velocity also westerly, minus 10 per second, suggesting that in the region of upper tropospheric westerlies, Doppler shifted group speed could approach 0. So westerly winds are going eastward, westerly group velocity is going westward. So when they meet, you have an opportunity for Doppler shifted group speed to reach 0. What does this mean for energy accumulation? So the determination of the zonal scale Kc at which the transition between easterly and westerly group speeds happens is straightforward, especially for the stationary basic state. This is accomplished by setting CGDX equals 0 in the relation for this. For u bar equals 0, the relation looks like this. So okay, so this is where the group velocity is reaching, crossing 10 meter per second in a westward direction, and that can meet westerly or eastward winds and create changes in waves to produce energy accumulation. What will it mean? How will that energy affect the dynamics? Those are the key questions we have to understand when you go for wave mean flow interactions and modulation of the wave number and frequency by the basic state. Okay, I think you get the idea of the physics we are looking for.